In the ceaseless whirl of Jovian clouds, there lies an ancient shadow etched upon the planet's face like a millennia-old scar, the Great Red Spot. It is not merely a vortex of gas, nor just another storm among the many that carve through the atmosphere of gas giants. It is an enigma. A celestial body within a celestial body, a wide open eye gazing into the universe, persisting, shifting, and baffling us. And yet, despite decades of space exploration and observation, one question, simple yet mocking, remains suspended among layers of ammonia and hydrosulfides. Why is it red? Anyone observing Jupiter through a telescope, whether amateur or orbital, cannot ignore it. They cannot avoid that striking vision, that crimson wound fixed at 22 degrees below the planetary equator, as though anchored to something immovable in a world of perpetual motion. And yet, there was a time when that spot was hardly noticed at all. Before the mid-19th century, no one seemed to pay it much attention. There were neither the means to observe it continuously, nor the habit of systematically recording its changes. Even when Jupiter's hue shifted, at times taking on an unusually reddish tone, not all astronomers agreed. Some saw it, others did not. And not by mistake. Color, like human perception itself, is as subjective as it is elusive. The turning point came in 1870, when Alfred Meyer, an American astronomer, observed a drastic change in the planet's chromatic appearance. Not only had Jupiter's bands become more jagged, but the entire globe appeared tinged in crimson, as if swept up in an atmospheric fire. Meyer reproduced these observations in a painting, the first known chromatic representation of the planet. And there, beneath the equatorial zone, one could unmistakably discern for the first time the ellipse we now call the Great Red Spot. Thus began the long scientific and technological journey to unveil the nature of this atmospheric monster. From the notebooks of 19th-century astronomers to the precision instruments aboard Voyager, Galileo, Juno, and the powerful eyes of Hubble and James Webb, the GRS, as it is often abbreviated in scientific documents, has become the undisputed queen of extraplanetary meteorology. Its longevity, its structure, its depth, its variations. Everything about it is studied, and everything about it remains, in part, an enigma. What we know with certainty is that the GRS is a colossal anticyclone, a high-pressure system rotating counterclockwise and rising about 8 kilometers above the surrounding cloud tops. Its outer winds blow at over 400 kilometers per hour, and the system completes a rotation in about 5 Earth days. But it is not merely a storm. On Jupiter's surface, its influence extends deep down, reaching some 300 kilometers into the atmosphere. It is like an invisible mountain of gas in perpetual rotation, an atmospheric summit immersed in an ocean of hydrogen and helium. And yet, something is changing. Year after year, decade after decade, the Great Red Spot seems to be shrinking. Today it measures about 16,000 kilometers by 12,000 kilometers, smaller than Earth's diameter. But in the 1960s, accounts describe it spanning more than 40,000 kilometers. A drastic contraction, almost alarming, if not for the fact that the very definition of its boundaries depends on a parameter as deceptive as it is mutable, its color. In fact, what we observe as the red spot is a combination of two structures: the central oval, the true GRS, and a surrounding region known as the cavity, which acts as a turbulent frame to the vortex's core. But both of these regions often shift in color. At times, the spot is clearly distinct, a deep brick red; other times, it appears paler, almost white or beige, blending into the cavity and even fooling measuring instruments. Some historical analyses may have mistakenly taken the cavity's dimensions for those of the oval, overestimating its size. The link between atmospheric dynamics and color has been explored in particular depth in recent years. A 2018 study revealed an intriguing correlation. When the GRS spins faster, its color darkens, becoming more intense. When it slows, it lightens. This suggests that its visible shade is not determined by chemistry alone, but also by physics, or more precisely, thermodynamics. The more energy the system holds, the more the molecules interacting with light may activate, producing different hues. But one fundamental question remains. Which molecules? For in the end, coloring an invisible atmosphere requires chromophores, chemical substances capable of absorbing certain wavelengths of sunlight and reflecting others, producing visible color. Nothing new here. The same principle makes Earth's sky blue, or Titan's clouds orange. But on Jupiter, things get more complicated. For decades, various combinations have been proposed: ammonia and acetylene, thiols, phosphines, sulfur, but none have yielded unequivocal signals in the visual and ultraviolet spectra collected by probes and telescopes. In 2016, an interesting theory suggested that photolysis, the breaking of molecules caused by ultraviolet light, might transform ammonia and acetylene in Jupiter's atmosphere into chromophore products. However, the amount of acetylene seemed too low to account for the observed intensity of the red. The search for the responsible molecule thus shifted once more. And so we arrive at one of the most promising hypotheses of recent years: ammonium hydrosulfide, a molecule with a simple composition, nitrogen tetrahydride sulfur monohydride, but an extremely complex behavior. According to some researchers, ammonium hydrosulfide may hold the hidden key to the Great Red Spot. This compound, formed by the union of ammonium ions, NH, and hydrosulfide, SH, is thought to be abundant in Jupiter's atmosphere in crystalline form, especially in colder, more turbulent zones such as the GRS itself. But the hypothesis is far from easy to prove. In the lab, ammonium hydrosulfide behaves like a rebellious substance. At room temperature, it is unstable. It tends to decompose into its constituent parts, making direct analysis difficult. At lower temperatures, like those expected in Jupiter's upper atmosphere, between -150 and -170 degrees Celsius, it becomes highly toxic and tricky to handle safely. Yet, by exploiting these extreme conditions, a team of scientists managed something extraordinary. They simulated the GRS's conditions in the lab. Using a sophisticated technique, they took crystalline samples of ammonium hydrosulfide, cooled them to near Jovian temperatures, and bombarded them with a proton beam, mimicking the effect of cosmic rays striking the planet's atmosphere. The results were surprising. The crystals, initially transparent and colorless, began to change. Depending on radiation levels and temperature, they took on shades ranging from yellowish to reddish to greenish. The key was perfect balance. Only when the crystals were hit with high doses of radiation and then warmed above the GRS's average temperatures did the resulting spectrum match almost perfectly with that observed in the Great Red Spot. But here lies a new problem. The surface temperatures of the GRS do not appear to match those needed to trigger the red color process. So, where does this transformation truly occur? One possible answer lies in the atmosphere's vertical movements. Ammonium hydrosulfide crystals might form deeper down, where temperatures are higher. Once generated and thermochemically activated, these crystals could be carried upward by the convective currents feeding the GRS. In this way, they would transport the pigment responsible for the crimson hue visible from Earth. But even this remains, for now, a hypothesis, elegant, suggestive, still far from definitive proof. There is yet another layer of complexity. The GRS is not a static environment but a system in constant evolution. Its shape, size, speed, and likely even its chemical composition change over time. If its color truly depends on one or more chromophores, it is plausible that these, too, vary with time. Other, as yet unidentified molecules may come into play, or sequential reaction mechanisms involving multiple chemical stages. The very chromatic variability of the spot across years could be the visible manifestation of an internal change invisible to our instruments, a real-time chemical mutation. Why, then, is all this so difficult to confirm? The paradox is that, though we have been observing the GRS for over 150 years, we remain outside spectators. All our data comes from remote instruments, spectrometers, cameras, radar. No probe has ever plunged directly into the Great Red Spot to analyze its components on site. Our models rely on reflected light, on signals processed from afar, on interpretive hypotheses. And every new piece of data, every tiny addition to the puzzle, seems to bring with it new questions. Another intriguing aspect is the GRS's relationship with Jupiter's other atmospheric bands. The planet is marked by alternating light and dark bands, each associated with high or low pressure zones. Storms and vortices frequently form within them, but none have ever reached the longevity or stability of the Great Red Spot. This suggests that the GRS is not simply another vortex, but something unique, perhaps sustained by exceptional conditions, or by a fragile yet enduring balance of physical and chemical factors. Some scientists have even hypothesized that the GRS originated in a traumatic event, such as the impact of an external body, perhaps a comet or a small asteroid, that triggered a self-sustaining atmospheric disturbance. Others argue it is endogenous, born spontaneously from the planet's internal turbulence. In either case, its survival is striking. In a world where everything shifts, moves, and disperses, the GRS endures. It changes shape, yes. It shrinks, certainly. But it does not vanish. And so, we return to the starting point. Why is it red? A question that seems banal, almost naive, yet encapsulates the full complexity of planetary science. It entails knowing the chemistry of Jovian clouds, the physics of storms, the interaction of light and matter across millions of kilometers. It requires instruments, models, intelligence. And perhaps, one day, it will require a direct descent into its winds, with a probe able to withstand the pressure and collect samples in situ. Until then, we will keep watching from afar. Studying it. Imagining it. The Great Red Spot remains there, a beacon of mystery in Jupiter's turbulent sea. A red signal reminding us how, even after centuries of observation, the cosmos can still astonish us with the simplicity of an unanswered question. If you have come this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.